Yes, we can. So, hello everybody, and welcome again to the One World Mathematical Game Theory Seminar. We are happy to have everyone here. We are currently 110 and still increasing. People from East Asia, from Japan, China, through the Middle East, to Europe, to Ehud Kalai, back in Chicago. So, okay, we don't hear you, Ehud, but you should unmute yourself so that we hear you. So anyway, we are happy to have today Jorgen Weibull.
I'm speaking muted, yeah.
Hi, Jorgen.
Hey, Shmuel. Hey.
Hi. Good to see you.
Good to see you.
Yeah, so we are breaking our high at 117, even higher than we had in the first seminar. So Jorgen Weibull from the Stockholm School of Economics. He has many contributions to game theory, and notably to evolutionary game theory. And he recently discovered the Homo moralis, which hopefully, as all of us, is driven both by selfishness and moral. And today, Jorgen will tell us whether we or moral people can play Equilibrium. So, Jorgen, it's your turn.
Thank you very much. Thank you for inviting me for this. I think it's a great initiative to meet like this, and I'm happy to talk. I must admit that I had a hard time to focus on a topic. I was so obsessed by this corona epidemic that I started to write an optimal control model for dynamic epidemic models together with two co-authors, Laurent Miclot, mathematician in Toulouse, and Daniel Spiro, an economist in Stockholm. So we have now a result on optimal control, and I was just obsessed by this. So I felt, what shall I talk about in games here now when this happens to us all? So I thought one topic maybe has some relevance also to today's situation with an epidemic, namely morality, because I think part of the things we should discuss is economics, of course, of these epidemics and controlling them and suppressing them, but also morality, because self-interest might lead to some sloppy behavior by some people, while some moral motivation might lead people to actually think about effects for society at large. And even if you think of yourself as being negligible, and I think there is a source of moral motivation in humans. And I will first talk about that from a theoretical viewpoint, and then I will also ask a question if we can see some of that in some empirical, in some data. And I have some experimental results. So I will be brief on that. That will be the introductory part to talk about what I mean by these things and what is the theoretical background for them, but that will be brief. And then I move on to this topic of question of existence of equilibria, because if one introduces morality in the way we have done, in this homo moralis way, you lose linearity in, say, finite games, and you introduce some curvature which is sometimes, hindering standard arguments for existence of equilibrium. So I will talk about that. That's joint work with Immanuel Bomse and Werner Schachinger in Vienna. We have a recently published paper. So I'm embarrassed that it's published, but some of the things are unpublished here also. So it's a mixture. Now, so let me start with the introduction. So I had some words in the title, moral motivation and so on. So when I talk about that, the interpretation here will be Kantian moral motivation. And I would argue then that there are theoretical reasons for belief that there are some such elements in our motivation. And I will also say that there seems to be at least some experimental evidence for them. Now, the answer to the question, does Nash equilibrium exist always, if players are partly morally motivated, will be negative. And what I will do is I will pinpoint some necessary and some sufficient conditions for existence and non-existence. So that the domain of games will be simple. I will talk about, although it can be extended, of course, I will talk about symmetric two-player games, finite two-player games. And that will be the domain today. And I will look at two information settings. One is complete information when two people who are equally morally motivated play a game. That is how we started out. And then look at incomplete information when there is a type distribution in the population and you know your own type of morality. You don't know, you know the distribution of other people, but when you interact with somebody, you don't know that guy's degree of morality. So this is the setup, and I will illustrate with examples and counterexamples. And if you have any question or suggestion or whatever, please don't hesitate to ask me. I will not see the hands being waved, but I think I will be helped with this so that I can hear you. So just you can unmute your mic, or we can also talk later. So I will be happy to do that. Now, so there will be three main questions here then. The first is what I mean by Kantian moral motivation and partly morally motivated players.
You're inviting interruptions.
Yes, but not too many. Yes, yes, please. Is it Bob talking?
One to start with, yes.
Yeah.
The Hassani viewpoint about randomization is that you do not consciously randomize. The randomization represents the other players' uncertainty about what you will do, but you do something definite. In fact, he has this model where there's some doubt about your utility function, maybe, okay, some epsilon doubt about utility function. And in that case, you may do something very definite, but other people don't know your exact utility function, so they don't know what they're going to do, and the randomization represents the uncertainty of other players about your
right.
Randomized, so that could be perfectly moral.
Yes, let me come back to that. I will indeed show towards the end in incomplete information games how we can think about randomization instead being deterministic behaviors of parts of the type space of players, for example. So I will come back to that. Thank you for your intervention there. Now, so one question is then what should one mean by Kantian moral motivation? Of course, this is a big philosophical question. I can only give it an operational meaning in the context. Second, about empirical evidence, I will give you briefly, very briefly. And then the third question will be the main question then. If we have partly morally motivated players, do Nash equilibria when they interact always exist? So here is morality in a person, Immanuel Kant, who said, act only according to that maxim whereby you can at the same time will that it should become a universal law. So this is when I talk about Kantian morality, I mean this is deontological morality. It does not think about in terms of empathy or sympathy or altruism, what happens to other people. When I do something, it thinks, what should I do if I want others to do what I'm doing? So that's a deontological motivation, and that is something I will come back to. Now, let's then look very briefly. I will not be long on this, and I will skip, quickly go through some slides just to motivate what is this homo moralis stuff. So there are two papers by Ingela Alger and myself. One is from 2013, the other from 16. In the 16 paper, there are n-player games. They are not finite games, these necessarily. There are two-player games in the first, n-player games in the others, and not necessarily finite, but I will now stay with finite two-player games. Now, in finite two-player games, we have a classical notion of evolutionary stability of a strategy. So if I write pi of x and y, as you can see here, as a payoff to a player using mixed strategy x against strategy y in such a symmetric game, that's the notation used by Maynard Smith and followers. So it's not player one and player two, but it's me and the other, okay, the notation. And then the evolutionary stability property then can be formalized in this way, which is equivalent to Maynard Smith and Price. It's not their definition. That you look at the strategy, pure or mixed, sitting in the simplex, unit simplex of mixed strategies in this finite symmetric game. And then you ask, okay, suppose a small fraction of people in this large population where we are uniformly randomly matched, they use some other strategy, y. And then we ask, is there an invasion barrier, a small epsilon bar, such that whenever this y strategy comes in a smaller population fraction, the people who do x, the residents, as we can call them, do better than the mutants, y. If that's true for all other strategies, y, then it's called evolution stable. And of course, many games don't have evolution stable strategies and so forth. Now, I will then move on. So instead of looking at evolution stability of strategies, I will look at evolution stability of preferences, under the assumption that people act rationally given their preferences. So imagine again a symmetric and finite game with payoffs pi, and I will call them material payoffs. I think of them as being utility from consumption or money, things like that. The setting is otherwise very much the same as in Maynard Smith and Price's model. There is random matching in a large population is imagined, the interpretation, but while they assumed uniform random matching, we allow in our work for some assortativity in the matching. So if you're mutant, it might be more likely that somebody you happen to meet is also mutant than the population average frequency. And I cannot go into the details of this machinery, but the assumption that is important here is that each individual is endowed with some continuous, what we call utility function here, function little u, that looks at strategy pairs, my own strategy and my opponent's strategy, and gives a real number, which is representing the individual's preferences.
Jorgen,
Mm-hmm.
I was disconnected for a while due to my Wi-Fi.
Yes.
So maybe this has already been commented or answered. Can you explain the displayed equation on the top?
Yes.
What is the y 1 minus epsilon?
Yes, I will explain this thing. So if you look at, I go back one slide now. So look at the lowest bullet point. Imagine now, this is just Maynard Smith and Price in nature, how they define evolution stability of a pure mixed strategy, little x, is sitting in the unit simplex of a symmetric two-player game. And if you play x and you meet somebody playing y, then your payoff is written as pi of x comma y. So your strategy first, the other guy's strategy second, not player one, player two. These are symmetric games.
Okay.
Okay, so that's a payoff, material payoff, utility money from consumption or something like that, or income. And then it says, now let's look at the strategy x, which we ask ourselves, could it be said to be evolution stable? And the definition suggested by Maynard Smith and Price is yes. The criterion they use is equivalent to what I've written here. It's not their criterion.
No, my question is, what is y times 1 minus epsilon times x?
Ah, that's a wrong notation. Thank you. Thank you. I didn't see that myself. So let me read that. Yeah. So x, pi of x, you play x, and you meet either a guy playing x with probability 1 minus epsilon, or with probability epsilon, somebody meeting y. And it should not be a y. It should be y, comma, and then the same thing, 1 minus x, 1 minus epsilon times x plus epsilon. So thank you. The second y should be deleted. It was a mistake. Yeah, typing. Sorry for that. Thank you very much. So this is the standard definition. Now we try to do the same thing, but in terms of preferences. So there is a space of preferences, and we imagine them represented by continuous functions, little u, that take any strategy pair to a real number. We require no connection with underlying material preference, just any continuous function will do. And then we imagine that this is the private information of the individual. That individuals strive to maximize the expected value of their personal utility function, given the matching protocol, which I can't go into here, random matching with perhaps some more assortativity, and the type distribution in the population, and they can then figure out the marginal distribution for them, what types they will meet. Now, if in that setting, one can define then a type u, a utility function or continuous function, as evolution stable against another type, or the same type if you like, but another type v, if there exists again an invasion barrier epsilon bar. And now the requirement is that individuals of type y, they should earn a higher material payoff than individuals of type v in all Nash equilibria, in all population states where there are only types y, u, and types v present, when the population share is 1 minus epsilon of type u and epsilon of type v. In such population states where there are only two types present, we say that it's evolutionary stable u if there is no Nash equilibrium when they play under incomplete information and they use their subjective utilities when they decide what to do, but we evaluate them in terms of material payoffs. There should exist no Nash equilibrium where the invaders or the mutants earn equal or higher material payoff. So this is, I think, what we found a natural extension of Maynard Smith and Price. Now, likewise, we say evolution unstable. So you have a type, utility function or payoff function U, which we say it's unstable if there exists some type V in the type space. That means any continuous function, such that whenever you look at any bound epsilon bar on invasion, and if you can find some population state with fewer people of this mutant type, so epsilon is their share, and some Bayesian Nash equilibrium in which they earn a higher material payoff, then we say they can be invaded by that. So there is unstable if there exists at least one type in some Nash equilibrium. Okay, so these are the definitions, and I will just do this rather quickly and give you suggestions for what could such functions be. And one function could, of course, be pi itself, because pi is a continuous function. We would call those homo economicus. So if you walk around in this population with pi as your utility, your utility function, we call you homo economicus. Or else, more generally, you could be a member of this family. Here's a one-dimensional family of functions. The parameter is kappa, a number between 0 and 1, and unit interval. And for any such kappa, we define the function as a convex combination of your self-interest, your material payoff, and this term, which is the payoff that you would earn if both of you, the guy you meet and yourself, would use your strategy, X. Okay, so if kappa is 0, then we are back to standard game theory with material payoff pi xy. If kappa would be 1, then we are what we call homo consciensis. These are people who take an action such that if everybody would take the same action, the same strategy, that would maximize the material payoff for everybody. So this is what we mean then by representing morality. We say that morality, we take it in this form. So on a scale between 0 and 1, kappa, it takes then the degree of morality, and that introduces, as you see, a quadratic term. In finite games, symmetric games as we have here, and X being a mixed strategy, you get pi xx, which is quadratic. So you lose the linearity there. Okay, so this we call homo moralis, having standard payoffs as one end at one extreme end, and fully moral motivation at the other extreme end. Now, the result we then established, Ingela, Alger, and myself, I gloss over many details here, is that this homo moralis type U of degree kappa, where kappa is adapted so it's equal to the index of associativity in the random matching protocol, that is evolutionarily stable against all behaviorally distinct types V. And all types U that are behaviorally distinct from UK are unstable. So it's a relatively strong statement. I cannot go into detail here about behaviorally distinct, but it has to do, of course, with the fact that sometimes you have the same behaviors, but your utility functions are different, right? So I will not go into that.
Can you please clarify what is this index of sociability?
Yeah, it says conditional on that you are of a certain type. What's the probability that guys that you meet are of your type? So that maybe that if you are then of a resident type, then maybe you are more likely to meet residents maybe than mutants, maybe, or maybe you're, and if you're a mutant, it could be that maybe your population share is only, let's say, epsilon, but we allow for the possibility that you're conditional on that you're a mutant, it's higher. And the reason for that is either genetics or sociology, if you like. So let's say genetics. If you take a kid who has a rare gene in the family, and then you say conditional on that this guy has a rare gene, what's the probability that the sibling has it? And then, of course, it is not epsilon, if epsilon is the general degree of that gene in the prevalence, but it will be roughly 1/2, right? If you have siblings over an usual sexual reproduction and equal probability of inheriting a gene from mother or father. So this is something that matters in biology, that if you interact then with siblings or kin, you have kinship relations, right? And that will become a kind of assortativity if you interact more with those. Likewise, we argue, if you interact within a language group, a geographical location, and things like that, it might be that you're more likely to meet mutants if you are yourself a mutant, because it might be local.
And you are adapting this to level of morality, so to speak.
Exactly, the morality will be adapted to that, because it says, because the genes are, so to speak, selfish, and they say, okay, hey, I'm a gene here, and I'm appearing in one individual, And it might be that there is some probability that another guy is also the same gene, and the genes are the guys who are the drivers.
Okay.
You could also say that if I take corona and you say that you have your condition on somebody being afflicted by this infection, the condition probability is probably higher that people that person is near to also are infected, right? Than if you draw a random person in the world, because we are not uniformly mixed in the world. We are interacting more locally with family and geographically and so on, right? So this is the result. So it says that if there is some degree of some positive index of assortativity, you get a positive kappa. If there is fully random matching, uniform random matching, then kappa is 0. So then you get selfishness again. Okay, so that was a theoretical argument and a description of homo moralis. Now let's ask the following question. Well, this was a theoretical result under idealized, of course, assumptions, but is there any empirical evidence? So there are 2 experiments that I have been participating in designing, one with Ernst Fehr and co-authors, which was recently published, and another one I will talk about also. So what we did here, we had data for master students in Zurich from ETH and also from the university, and we let them be matched to play a sequential prisoner's dilemma. So one moves first, and the other one gets to know if the first one chooses D or C, and then chooses conditionally C or D. Now this, you can say, is not a symmetric game, but we symmetrized it by saying that first we pair people. So we say you 2 guys will play, and then we toss a coin, who will be the first mover and who will be the second mover. So that game then is symmetric, and that's what we analyzed. And then we found the following, that we ran a horse race. One model was inequity aversion, Fehr-Schmidt. Another one was modeled by Rabin and others on conditional welfare reciprocity, and I cannot go into that. And an old model was altruism, Becker, that you care about the payoff to the other guy. And Homo economicus, of course, is one model. And then Homo moralis, and what we did is we took each model and use the data to give it the best chance, and then we see how well can Homo economicus explain the behavior in the lab, and it could explain 28% of the data we saw, and you can see the numbers there. So Homo moralis did well; it explained around 70%. Then we did the following: we used a Zelten-Krischker score, which means that you adapt the hit rate to the surface of the goal. Because if you have a theory which says that anything can happen, then you will have a 100% hit rate, right? If you have a very precise theory, you will have a small hit rate because the surface is small. So Zelten and Krishner suggested some axioms whereby one could adjust hit rates to the model's precision. And then you got this Zelten-Krishner score, and then you see the numbers are lower, and you can see that Homo moralis does well there also, right? So it seems to have explanatory power. So that we thought of as justifying it to some extent, that we see it. And now we have some ongoing experiments, which we just finished, and we are now making estimates and so on. This joint work with Boris van Leuven, experimentalist in Tilburg, and Ingela Alger and myself. And it's a working paper that you can look at if you like. We had more subjects, 136 master students. They are from Tilburg. And we asked them to interact in 3 classes of simple sequential 2-player games. So they're, like trust games and so forth, symmetrizing them in the same way. And then for each game class, we gave a variety of different monetary specifications. And then we ran the data. And if you look at the little diagram, if you can see this here, it should say on the horizontal axis, the estimated kappa value for an individual. So using an individual, we observe this individual in 18 different interactions. And we also have elicited beliefs and so on by the individuals. So then you can see that it has a distribution which looks a bit skewed, but it is clear that it's not only that people sit at 0, but they sit usually with some positive degree of morality, helps to explain the data. So again, there is some evidence, and we have, of course, much more to say, but I will just say this, that there is some evidence for some degree of morality when you want to explain experimental behavior. We don't have any field data. So that leads me then to the third question, which is the main question for today, namely that if players are partly morally motivated in this sense of, with homo moralis, what can we say then from game theory viewpoint? Do Nash equilibria always exist? Okay, so now I'm back to the question, and I will analyze this question, discuss it for finite and symmetric two-player games. First, complete information when two equally moral players meet, and then incomplete information when people know their own morality, but they don't know the others who they meet. But they behave as if they would know the type distribution, the distribution of morality degrees in the population. So is this okay? Everybody is okay? I cannot see you or hear you, but I hope that you are still there.
Oh, yeah.
Are we doing fine?
Well, you can't see us?
No, well, I can if I look, but I need to see the screen also. So I can see, let me see, I can look at, now I can see you, yes. Okay, so very good. So, okay, so this was the background. So let me now go on and look more at this. So this is the recent work with Manuel Bomse and Werner Schachinger both in Vienna. And we just published this in Economic Theory. So what is the situation now? Now I'll be a little bit more formal and try to pin down more clearly the results we have. Okay, so let capital S be the set of pure strategies, finite, little m pure strategies, and it's a symmetric two-player game. And let delta be the unit simplex. So these are vectors x. And I will use column vector notation. So E is here the vector with ones in it, and EI is the unit vector for pure strategy I, so like playing pure strategy I, and E is the sum of those then, and so on. And I using then a transpose here to denote when I turn it into a row vector and so on. Okay, so that's it. And then there will be some payoff matrix, which I will denote capital A, an M by M matrix. And we will think of them as, I will talk about them as kind of material payoffs, if you like. And pi will then be the same function as used by Maynard Smith and Price and so on. So pi of xy says, what is my material payoff if I use x and I meet somebody using y? So then pi xy can be written then as the transpose of my vector x times the matrix A times the vector y used representing the other guy's behavior. Now, let theta now be a player type. This is like I called kappa before. So then let's look at a one-dimensional class of payoff functions, u of index theta, defined by this little equation 1 here. So it says a guy of type theta places weight 1 minus theta on his own material payoff and the complementary weight theta on the payoff he would get if both of them would use his strategy, right? So this is then in a slightly different notation, the homo moralis of degree of morality theta. So theta is 0 is standard payoffs. Theta is equal to 1 would mean I'm looking at what would maximize payoffs. Now, this is a symmetric game, so the payoff matrix by the other player, B, is the transpose of A. And then if we talk about welfare, which I will do here, we will just think of it as a sum of their payoffs, so X transpose times the A plus A transpose of Y. Okay. Now, of particular interest for the analysis that comes is when both players use the same strategy. So therefore I define now the function, the welfare function W defined on the simplex of mixed strategies as the payoff to a player who uses X if the opponent also uses X. So that will be then the sum of their payoffs will be 2 times that. And then we can rewrite, this will be convenient in the subsequel, the payoff function for type 1 theta player, namely the first term is the own payoff, 1 minus theta times that. And the second one is theta half of this welfare function, right? Okay, so far mostly notation and things. Then beta theta will now be best reply correspondence, which says if I best reply to any mixed strategy Y and I'm of type theta, what will I do? Well, I will do something that maximizes my utility function or my payoff function here down here, choosing an appropriate strategy X. Okay, so that is the best reply correspondence. Now, if we look at that and we think of Weierstrass, that is fulfilled, right? So this is a compact space I'm drawing from, and this function is continuous. There exists a maximizer, and it will be a non-empty compact set then of best replies for every theta. It doesn't matter if what theta is, and it doesn't matter what y is. But as we will see below, and as you expect, this set will not always be convex. Okay, so now the set X, capital X of theta, those are the strategies that are best replies to themselves. It should be an X. It says X belongs to beta theta of X, not Y. That's a typo again. So these are pairs. If you look at such strategies, you take any strategy in that set, which might be empty for some games, that would be then a symmetric Nash equilibrium between two homines morales. If you do the Latin plural correctly, I learned that, should be like that, of the same degree, right? Now, if we now want to go for equilibrium, it's natural to call in Claude Berge, and then we look at beta of theta, and it will be, of course, upper hemicontinuous with respect to both y and theta. Was there a question or no? So this will be compact valued, upper hemicontinuous, but as I said, maybe not always convex valued. Okay, so now let's start with equally moral players and then move on from there to incomplete information. So now if it is the case that theta is either 0 or 1 at the endpoints of this interval of types, well, then the set is non-empty and compact. And that is standard, right? Not surprising, because in the first case, when theta is equal to 0, that's homo economicus, so only caring about my material payoff, the usual payoff function. Then we have, this is Nash from Nash existence result in Kagetani, if you like. There exist Nash equilibria for types 0, of course. And if theta is equal to 1, that means if players don't care about what other people are doing, they just want to do something that maximizes this welfare function. It's a continuous function. So again, the set x theta will be non-empty. And of course, if now w is a concave function, then this is true for all theta, right? I go back to this equation so you can see it here, because if you look at this thing here, the payoff function the payoff function here is a linear combination. You take this linear function, and if you add a concave function here, you get, of course, a concave function, and then everything is set by standard arguments. So then we would have existence again, right? So if W is concave, then everything is fine, and we are back in standard. Although there might be a preference then for mixing, and we come back to Bob Aumann's point later on about that. Now, a sufficient condition then, if you want to know when will we know if W is concave, well, we can of course look at the symmetric matrix A plus this transpose and ask if it's semi-definite, negative semi-definite, then it will be concave. But that's sufficient but not necessary. So I will come back to necessary and sufficient conditions for W to be concave, or else to be strictly convex, both of those cases. Okay, so this was some observations, and then let's look at some examples. So take a simple little coordination game where two people play, and they can take the first strategy, pure strategy, and earn A, both of them. Or they can, both of them take the second, they would earn B, and we assume B is less, but both are positive. So they want to coordinate. Okay, and then if I take the type 0, so it's standard homo economicus, then of course there are 3 fixed points. One is to play the first pure strategy, the other one is to play the second pure strategy, and the third one is a mixed strategy that makes the players indifferent, and that mixed strategy will then be algebraically given by the x star. You see that vector there. Now in this case, W is strictly convex. You have, two, you can see it's lowest in the middle and higher up on the corners. And then in that case, when that is the case, then best replies will be sitting in, for people with positive theta, your best reply will be a pure strategy. And one can play around with this. It's easy, vary theta. And what I would show you, I think is maybe more illustrative, is this diagram. So if I vary now theta here, on the horizontal axis from 0 to 1, and then with the red I indicate the equilibrium correspondence, looking at x, the first component, x1 or x star 1 if you like, and the fixed points set. Then if theta is 0, we have 3 fixed points as we expect, the standard thing. Then I increase theta, and for small theta, the two pure equilibria remain, but we lost immediately the mixed equilibrium as soon as theta was positive. And then at a sufficiently high theta, and in this case it is 1/2 because I've chosen these numbers you see down there, then the inefficient pure equilibrium disappears. People are sufficiently morally motivated, so they will go for the best of the 2 pure equilibria. Right, so for high theta, they will play the best equilibrium, pure equilibrium. For no positive theta will they ever play the mixed equilibrium. So this then shows that the mixed equilibrium in this game is non-robust to small degrees of morality. So while it is a well-behaved equilibrium in terms of perfection and properness and strategic stability, the mixed equilibrium, it survives all of those. It doesn't survive the slightest degree of morality. So that's the equilibrium correspondence for that example. Kind of polar case is the Hawkstaff game. I just moved around the A and B and put them off the diagonal and still imagine that they are positive. And in that case, the symmetric matrix A plus AT is indefinite, but W is strictly concave. Then y theta, u theta will be concave, so there exists at least one fixed point. And it's easy to compute it. It is this thing here. So it says, when theta is 0, we know it is A divided by A plus B for the first component and B divided by A plus B for the second. And then if there is a positive theta, you have to add some of that also. And I draw a picture again here. You can see here at the top, varying theta. This is the equilibrium correspondence expressed in terms of the probability placed on Hawk on the first strategy. You can see it's this curve here. So there's unique equilibrium for Homo moralis. When theta is 0, it is the unique symmetric equilibrium, standard one, which was also the prime example by Maynard Smith and Price, by the way. And for these numbers, it will be this sitting here. And then, as you can see, it is then continuously moving down towards 1/2, 1/2. So when people are fully moral, they will use the aggressive Hawk strategy less, and they will randomize 50-50. Now we had concavity, so they were happy to do that. Okay, so now one class of games that we have studied a lot in game theory, and you guys have done fantastic contributions, is zero-sum games. Now this is a simple class of zero-sum games, of course, but still one can say something of some interest, namely that if the payoff matrix A represents a symmetric constant sum game, or zero-sum game if you like, then of course Wx is a constant. So therefore, as soon as the degree of morality is below 1, the set of fixed points will be the same as when people are selfish. While if we let theta be equal to 1, then anything is a fixed point. So the equilibrium correspondence then is like that. And that is something which I think is interesting. So if it's a perfectly, so to speak, competitive situation, zero-sum game or something like that, then it does not matter what degree of morality people have as long as it is below 1. They behave in the same way. So there's no effect on their behavior or equilibrium by morality. Except for the extreme case, which I think is probably non-relevant empirically when people are fully moralistic. Now, so we have now to study when W is not concave, as it was in one of our examples. And I will turn to that by an example again. So simple example, a generalized rock, scissors, paper game with payoff matrix A, and where there are the usual payoffs of 1, 2, and 0. So 1 for a tie, 2 when you win over the other guy, and 0 if you lose. But with added a little quantity A to the winner. Okay, so rock, scissors, paper. So the rock meets the scissors. the rock wins and earns 2 plus A, and we assume here now that A is some number that is greater than -1. So it could be 0, of course, and it could be, you know, also positive. Now, in the case when A is 0, it is a constant sum game, so then everything holds what we have said. And also we know that for the standard case, when theta is 0, so we have Homo economicus, there is an equilibrium and a unique equilibrium, and that is 1/3, 1/3, 1/3. But what we know also from evolutionary game theory is that this equilibrium is unstable in the replicator dynamic if A is negative, and is asymptotically stable if A is positive. So when A is positive, behavior swirls in towards that barrier center. When A is negative, it swirls out from it. And that this will be reflected now in the results here for moral play, actually. So we look at the function W defined before, the welfare function. If one can write it up, and one gets the formula after some algebraic manipulation, you get Wx is some constant plus A times this term 1 minus x norm squared. Okay, so that if A is positive, then this is a concave function. If A is negative, it's convex. Right, it's strictly convex if it is. So this is now what we then find is that if it is negative, so that would be, this point would be unstable in the replicator dynamic, then also this will not be an equilibrium for moral players. So when A is negative, one can look at what happens. Then best replies will sit on the vertices. People want to move out to pure strategies. And one can make a simple calculation here to find out that no vertex is a fixed point. So there is no fixed point at all in that case. So A negative and degrees of morality strictly between 0 and 1, there is no symmetric Nash equilibrium. Okay, so that then asks the question, can one say something more general? And here is a proposition which says, well, take any game now, any symmetric two-player game, finite, and then suppose that we know that W is strictly convex. Then the same thing holds, that best replies will be pure. And one can then ask, you know, if any one of those vertices is a fixed point by simply comparing the payoff when using that to the payoff if you deviate to some other pure strategy K. But also what would happen if not only you deviated, but both deviated to K, because this is moral play, right? So this explains the right-hand side. So for theta equal to 0, which is the usual thing, it's just a Ki. What can I gain by going to pure strategy K if others are playing I? But now I have to add also what happened if others would do what I'm doing, and that gives the theta times AKK. So that's a little, a little result. And then, you know, how useful these are will depend on how easy it is to figure out if the welfare function is concave or strictly convex on the unit simplex, because remember that the welfare function is defined on the unit simplex, right? And here is a result, which is algebra, which is simply to take account of the fact that we move on a hyperplane that contains the simplex, and then some algebraic maneuvering, which I will not go into here. One can add a column and then get a matrix C, and then concavity holds if the matrix D, which is symmetric, is negative semi-definite, and W is strictly convex if it instead is positive definite. So this is a criterion that one can use. One can actually calculate this relatively easily for any given game. Okay, so now I will say a little bit more about the case of play between equally moral players and the complete information. And one class of games are potential games, which here would mean that A is itself a symmetric matrix. So we know then from evolutionary game theory that if you run the replicator dynamic, then the average payoff will increase along all solution trajectories. Now, similar results hold here, so that what happens then is that if you, no matter what is the degree of morality, if you have a global welfare maximizer, some point x which maximizes w, then that will be a fixed point. Moreover, if you have some fixed point, it must be at least a local maximizer. So this is stated here in A and B, right? So, and if we take a coordination game that we looked at before, then, you know, to play the first strategy, which gives the payoff 2, would be a fixed point. And the other one says that if you have something which is a fixed point for some theta, it must be at least a local maximizer. So this then relates a bit to actually evolutionary results, game theory results, and also for cheap talk games, actually. There are some connections. I don't know anything deep about that, but I mean, we find similar structures here. So this was what I was going to say about complete information, and now I will talk about incomplete information. So is there any questions so far, or? No? I go on then. So now let's look at these players who are of some, you know, they are all homomoralis, but of maybe different degrees of morality, and you know your own degree of morality, your own kappa, if you like, or your own theta, but you only know the population distribution mu over the type space when you meet people. So let mu then be a Borel probability measure on the type space. And then what do we mean now by strategies and equilibrium and so on? We will, this will be the, what you would expect, I think. So what is strategy? It would be a Borel measurable function that says, if I know my type, what mixed strategy will I play? Right, and we call that psi, you know, it's like a Greek x, if you like. So psi of theta is the x that I will pick if I'm on type theta. Now, what do we mean by optimal? Well, we say it's what we would expect. It says that it is optimal against the mixed strategy. You meet, if you would meet strategy Y, then your strategy, the strategy X says for each type that you might be of, do the best thing, right? So that defines what is an optimal strategy. Now, the question then is, do these exist? Because we cannot assume continuity here, but they will exist. It's an application of a selection theorem by Kuratowski and Ril-Nardzewski, which asks for measurable selections from measurable correspondences. And the conditions are then met. So such optimal strategies in our setting will exist. So if you have a player and you ask who goes in there, and you want to find out for each of the possible types he might be, what should he do if he meets strategy Y? Well, that exists, that object. Now we can then ask about equilibrium. So what does equilibrium mean now? Well, it means that such a strategy Xi is the best reply to itself if the following holds. If it says, well, it should always do the best, it should choose the best strategy X when it meets somebody in the population, and the population is using strategy Xi. So you say, what will type tau do? Any type in the population in this type space. That type will do Xi tau, right? And then I will get payoff u theta of X, which I use, and Xi tau, what the other guy uses. And I just integrate over all types tau according to the measure mu. And I want to do well in this expected utility maximization sense, right? So this would be the natural definition of a Nash equilibrium, a symmetric Nash equilibrium, right? A pair X psi xi would then be an equilibrium pair. Okay, but then there is a very nice feature of two-player games, finite games in general, namely linearity. So if we look at the payoff function u theta of X, when I use X and the other guy uses Y, it is linear with respect to Y, right? Because u theta of X and Y was first the usual payoff function, which is X transpose matrix A, Y, linear in Y, and the second term contains only X. So therefore, if one integrates u theta with respect to some strategy Xi, one gets u theta of X and Xi bar, the average value of Xi, the average strategy. So this is the representative agents mixed strategy when Xi is used.
Jorgen, you have
Yes.
10 minutes.
Okay, thank you very much. So thank you. So that so this is a nice linearity which we will use. So you can only, it's enough for you to think about, you know, if you take a Xi, I calculate what is the average play of those guys. That's enough, right? Now, so that is then says that we can then go ahead and study existence of symmetric Nash equilibrium, but it's still non-trivial, because we have to look carefully at, we are working on a simplex in an arbitrarily dimensional space, and we have a function that's quadratic, linear quadratic. So what one can do then, and this is much thanks to my co-author here, Imal Bomze, who is an expert on optimization, and in particular linear quadratic such, that one can characterize Nash equilibrium by way of a first order condition, and a complementary slackness condition, and a second order condition, which is not standard. So this is a relatively recent publication by him in a operations research and mathematics journal. And the reason why that is also sufficient, the curvature, is that we have polynomials of degree 2 only here. So we don't, so this is then possible to do, and then the result will be stated as theorem 2.6 here. And it's a lot of algebra. One has to first figure out the Hessian, which one can do a linear algebra thing, and then gradient of u theta evaluated at the strategy where it applies, and then do updates of the Hessians. One has to take count of the that we are on a simplex. So one has to, when we define, you know, convexity and concavity properties, we have to do it restricted to the simplex, which is sitting there on this hyperplane. So one has to be careful, and there will be a polyhedral cone. E with a sign orthogonal there are the vectors that are orthogonal to the vector E, which means these are points lying in the hyperplane. So we look at that hyperplane, and that's the cone. And then one can state the result that for any Borel probability measure mu, no matter what it is, strategic psi is the best reply to itself if and only if there are Borel measurable functions lambda I that to each type theta does something for each for each strategy I, and also for I equal to 0 for normalization reasons, such that the following holds here, and these are the Lagrangian. There's a Lagrangian equation, there is a complementary slackness condition, and there is a curvative condition. So that then can, in principle, be calculated and checked, these conditions. And that will then tell if there exists, if this is a fixed point or not. I will just now return to the example where we had the the rock, scissors, papers game with no equilibrium under complete information and equally moral players. So assume A is negative and theta is strictly between 0 and 1. There was no equilibrium in that game. Now, one can then view this, of course, as a game of incomplete information, but with a Dirac pulse unit measure sitting on a particular type theta, right? And then one can ask now, is this non-existence, is it robust if we allow for some uncertainty about the type distribution? And the answer is no. Because what we can do then is to say that, okay, let's instead take any continuous type distribution, mu, and if it's, so it has, it will be absolutely continuous, so there will be a density function. I will come to proposition. I just make it for an example first. So one can think of cutting up the types space into 3 equal chunks, 1/3 of each, and then in that game that we looked at, Roxy's paper, let those in each category K of the 3 categories, they play pure strategy K, and then they all best reply to the average play, which will be the barycenter. So that suggests then that if we would take any continuous distribution, which in the sense of L1 norm is close to the Dirac pulse, we will have an equilibrium. And what will happen is that they will play, the behavior that you will see in the population is exactly the barycenter. Now, this can be stated a little bit more generally, which is done in my last proposition here. So it says, suppose that we have a situation where the welfare function is convex, so it's a problematic case. But now assume that mu is absolutely continuous and it has a probability density function that it can represent it, f. Now, if there exists some strategy so that its support coincides with its pure best replies for all types, for theta and tau, then there exists a Nash equilibrium, and what will happen in that Nash equilibrium that they will play as they will materialize, they will realize this X. Now, and then it might seem to be a knife edge condition that they should agree, that the support of a strategy should be equal to its best replies. But since these are pure best replies, they are constant almost everywhere in the type space. So generically, to keep three things constant is holds generically then. So it's not as demanding as it might look, and it is met then by this example. So this suggests then that a little bit of uncertainty about the types can help to get equilibrium. So if I conclude here, and then I'm willing to discuss, of course, and happy to have questions and suggestions. I hope that I've answered what is meant by what I mean in this discussion, Kantian moral motivation and partly morally motivated players. And I think I've suggested a positive answer to the question if there is any empirical evidence for such motivation. It seems to be the case. And then the third question, if players are partly motivated, do Nash equilibrium always exist, has been answered negatively. But then with some necessary and some sufficient conditions for many cases where we can pin down existence or non-existence under complete and incomplete information. So that is the end of the talk, and I thank you for your attention.
Thank you. Thank you.
Any questions or comments?
Yeah, I have a question. This is Bernhard from...
I'm sorry, I couldn't hear there. Yeah, once more.
Okay.
It's too loud, the voice, the sound. I cannot. It's distorted sound.
Okay, so is it better to hear now?
No. Somebody, no.
There is some distortion on the sound.
When I talk?
Can you diminish your microphone? Maybe that would help.
Turn it louder. Is that better?
No.
Sorry.
Bernard, you're too loud. We cannot. I mean, it's a music for a wedding or something.
Okay. Serious.
I cannot hear you well. Sorry.
I think the organizer should mute everybody and only the one who speaks, let him talk.
Okay, good. Yeah.
Okay. Bernard, maybe you want to type the question?
He has muted his mic now, right? Yeah.
Yeah, but there is a chat. You can type maybe.
Yeah, right.
If the sound doesn't go well.
Jorgen, let me ask a question in that case.
Yes.
What happens? So here we speak about two-player games, symmetric games. Did you think about morality in n players? What should morality mean?
Yes. So let me mention that to you. This is what you do. What we do then in that study is to say, suppose you have symmetric games, not necessarily finite, but symmetric n-player games, so that your strategy space is some topologically well-behaved vector space, maybe a simplex or something like that. Then what it turns out, if one does this evolutionary argument, the same argument, and the same requirement that there shouldn't exist a mutant type, a mutant payoff function, such that if it came in would earn in some equilibrium a higher material payoff essentially. That turns out then to work if we do the following. If we assume that the payoff function not only is continuous, as we have done so far, but also that it is aggregative in the sense that if you get your material payoff should depend on your strategy and on the other guy's strategies, but it should be permutation invariant over the other guy's strategies. So that if the other guys, if you choose X and there are other players, let's say Y1, Y2, and Y3, and so on, your material payoff, if it doesn't depend on which order you take these, so it only is so it's aggregate invariant. For example, the sum of them, sum of contributions to public goods, or the product of them, or the minimum or the maximum, things like that. Then one can do the analysis, and then it turns out that the homo moralis can be defined in a generalized way. So what essentially it does, it says that homo moralis treats the strategies of a guy he meets as a random variable, which can be written as a random draw that for each individual he meets has some probability of being his strategy and a complementary probability of being the one that he has been expected to use, so that it is a smooth function with very much the same properties for n players. And then you get this instead of now we had quadratic forms, now then you could have cubic forms and so on, and we don't have any analysis of existence of equilibria then, and that would be a wonderful thing to see. I mean, I would be delighted if anybody has the energy and interest to look at that. May I add one more thing? If the number of players, if I call that n, so n is equal to 2, that's what I did today. If n is 3 or 4 or 5, then it's a lot of combinatorics when you write down this formula. So it's a combinatorial formula, an expectation. But if n is very large, then we can use this theorem, Laplace theorem, which says that it will be very well approximated by a normal distribution, actually. So one can then, if we have continuous payoff functions and so on, you can approximate the payoffs by a very simple thing, which means it is as if you imagine the proportion of other people, kappa, does what you are doing. That would be a good approximation for large n. And I did numerical calculations showing that if n is just bigger than 5 or 6, it looks very nice. I mean, so it seems to be a good approximation for games with not very dramatic payoff functions, at least.
So I have a question, if I may. I don't know.
Yes.
Can you hear better?
No, it's very loud still.
I don't know what this is. Sorry, so try to speak louder.
Yeah.
Bernard, you can type the question in the chat.
Can you hear me now? I mean, is it loud still? Hello?
It doesn't work too well.
Is it very loud or something?
I can read chats now. Okay.
Okay, sorry. I type. Yeah, sorry. Just have to.
I see a question about non-symmetric games. Can I answer that now in the meantime, or is that okay? Yeah, okay, so there's a question about, I don't know how to do that. The only way we do it then is by using the wheel of ignorance instead of Harsani and so on. So if you have an asymmetric game, as I suggested, a game where somebody moves first and then another guy, if you think that everybody is equally likely to be in the first role as in the second role, then of course you get a symmetric game. So by symmetrizing it, by saying that under a wheel of ignorance, you don't know which player role you will have, then you get a symmetric meta game, if you like, and then morality can be defined. That is all I can say. I mean, that's what I know, and I don't know how to get further. I mean, Harsani was struggling with these things also from another viewpoint, from welfare theory and moral and so on. And if anybody has an idea, but that's, you think of yourself as being in different player roles, and then you say what you would do. That is a symmetric game. We can then do the same thing. But yeah. Is there another question? I don't know, Bernard, did you write down a question or?
No, I'm still what about the sound now?
Is it better?
This is good. Yeah, this is good now.
Yeah, sorry, I was messed something up, and even rebooting didn't help. My question is, did you talk about this with any Kantian philosopher? I'm asking because I have a colleague who I asked the following question. In old trains in Germany, you said you had a sign that says, please leave this bathroom in the state in which you would like to find it. In other words,
yeah.
not only, even if it's ugly, I mean, make it neat afterwards. Sounded very German to me. And I said, this sounds like a Kantian principle. And I wonder, and she said, no, Kantian is much more strict. It says it has to be a law. Act as if the way you behave could made into a law of moral behavior rather than just as if everybody behaved like that.
No, so, that's true. Of course, there is an enormous literature in philosophy on Kant and other moral systems. If you look into history of human history, you will find all kinds of codes in different cultures. The oldest I've found is, I've heard of, is some scripts from Egypt, which are like 3,000 before our time area, and they say something, not so different from Kant. Then there are other ones like golden rules, but they are not the same thing. So that the Kant idea is, I think, important that it is a kind of a universalistic idea. But of course, if you apply it very strictly, and you want to do this very carefully in some examples, it becomes very hard to say exactly what it should say.
Okay.
I mean, one classical example against Kant then would be that suppose there is a killer coming in and who will kill your friend or whatever, your children, and he asks which room are they hiding in? Should you lie or not? Because if you say that, you should never lie. If that is then that's a dilemma, and so on. So there are, and then so there are lots of discussion of this. So I think it is a rather difficult to pin down. What I like with this is that it was the pure mathematical property. It's not a question of interpreting what should we mean by Kant. This is a mathematical function, and one can think of it as an application of Kant, but it is not that I don't have to philosophize. I have to just do the calculations. So it chooses a kind of a utilitarian criterion, right? Because it says what it would be the payoff if we both would do something. So it kind of connects utilitarianism with Kantian, and I've never seen this before. So I can imagine some philosophers will object to this and say it's too much utilitarianism or something, but but I think it's important that it's deontological, it's non-consequentialistic, because when you think of the second term, you don't ask what would be good for the other guy. In a coordination game, maybe the other guy is using some inefficient strategy and you're sufficient moral, you will not coordinate with this guy. He will be angry at you because you will take a better strategy if both of you had used it.
Jorgen,
yes.
Is there a way to derive Kantian morality or any other kind of morality from evolutionary considerations?
So what we did was we did it by generalizing the definition by Maynard Smith and Price, and we got it. We have also done another study which is much closer to evolutionary biology, modern one. We worked together with a very good modern biologist, Laurent Lehmann in Lausanne, and we published that paper recently, where we use instead a stochastic process which they use in biology. So individuals live on islands, and sometimes their kids migrate between islands, and you write it down like a Markov chain, and then you put in one microbe, like a one corona virus in one individual, and you see if it spreads or not. You do this with types, either strategies or types. So we have actually solved that model, and we get very similar results. But the arguments are not at all topological. They are just have to do with reproduction rates and stochastic processes. So I think that would be probably what biologists would find most closely related. So we have two papers, one biological there is a journal called Evolution, where we publish this, where we do the biology version of this, and then we have one also published in an economics journal where we do the economics interpretation. So we are trying to connect. Some biologists like it, some they think it's too mathematical and too abstract or whatever. So
well, what is really the conceptual conceptually, what's behind it? I mean, why evolution is about survival of the fittest.
Yes.
Do you tie this to survival
absolutely.
of the fittest, either on the individual plane or
absolutely.
on the group plane, or what?
Absolutely. So that you're absolutely right. So that it is absolutely Darwinian. In this case, you can think, if you think of genes, they use us as machines for reproduction simply, right? So we are just tools for them. And the same thing is here. Utility functions or strategies, they jump around, and those that manage to spread or don't spread, that's what matters. And in what we assume then, if I take this biological model, which I did not talk about today, we imagine then that if you have a trait, a type, which can be a strategy or an attitude, moral attitude or whatever, if it benefits the survival, reproduction and survival of the individual, then it has a higher probability of staying around, right? And it will spread. So we take the material payoffs and say that suppose that material you have a higher chance of surviving if you have a higher material payoff than a lower one. So that's what we do. So we connect the material payoffs to help propagate this virus, if you like. Maybe it was a virus instead, of a utility function. So there is a connection, absolutely.
All right, we have to.
Bob, think about it in the following way: that if we talk about moral values or utility functions, suppose they spread in families. I mean, for being simple, so that you have values, they spread to your kids. So if it is, some of your kids will share your values, they're influenced by you, and then they will be like each other when they interact. Maybe they interact with other people who have maybe similar values to theirs. So that will help that value. If it is a constructive value, it will help those who interact and have the same value. If it's a destructive value, it will not help them. And
so it's some kind of group selection.
No, it's not at all group selection. It's not at all. It is not group selection. So this might not be.
I don't think that's a dirty word. Yes, I think.
No, I know, but it is. I know, because if you say group selection in biology, they kill you, right?
No, not necessarily.
No, not nowadays.
But there's a fairly respected, or I don't know whether it's respected by all the biologists.
No, but that's true.
Respectable group of group selectionists.
I know. It was Maynard Smith who wrote a model which was called the haystack model, right, in 1961 or something. And that, since then, biologists were scared to death to mention group selection. But his model was tilted, I think. It was actually flawed, I think, in a certain way, which we cannot talk about now. But this is not group selection. So it's not I do what is good for my group. It is simply the genes are selfish. I mean, the gene is now a utility function or a value or a strategy, and it thinks about itself only. And then if there is some associativity, either because there's an island structure or some other structure, when it interacts, it knows, it so to speak, is as if it would know that it might be interacting with itself. And that's what matters. So it's self-interest from the viewpoint of the utility function, if you like, or the strategy or the gene. And we are just carrying these things.
All right.
Are there more questions?
Last question.
Well.
Can we rank country? Did you do experiment to rank countries or some countries with regard to their morality?
What we can, this is a fun question. One could also ask about other differences, age, gender, whatever, culture, country. So we do have this setup for lab experiments. We have done it in Tilburg and in Zurich. And my impression is that people in Tilburg are slightly more self-interested and less moral a bit. Maybe I'm just saying this without any statistical careful study. But what one can do is run some experiments, with games which are like allow for trust and cooperation or whatever conflict, and then estimate the parameter distribution for the kappa, and then find maybe that there is a difference between countries. I would not be surprised. What our theory says, if I now go to the biological theory that we had developed, is that you will get more morality if the society is more localized, so people interact more locally. And another factor that matters, if there are conflicts between different societies, We do that. We have a paper called Guns and Jeans, in that style, title in Jet recently, where we show that conflicts between groups will foster actually a form of altruism between them, which is not surprising. So, there are reasons to believe the history of our history, culture and history and geographical history. The history of Sweden has not been to war for 300 years. It invites Corona to come in rather freely, right? We have also liberal immigrant policy and so on. And then you have other countries who have been into conflicts and so on. So I think it can matter, and the amount of trust and so on. So I think there will be differences. I wouldn't speculate, but one can essentially set up a lab and test, if you like.
Okay, so thank you very much, Jorgen.
Thank you all.
Yeah, very interesting, very moral.
Thank you very much for your comments.
Thank you all.
Thanks.
See you again in 2 weeks.
Thanks to Elon. Thank you, Elon, for all the work.
For organizing. I think it's a wonderful idea to organize this. This is a great thing to do. Yeah.
Yeah. This is a joint endeavor with Paris and Budapest and Maastricht and Bar Ilan. So we are very happy, and we will be happy to have more people join in our management.
Excellent.
So goodbye all, and in 2 weeks we will have our next seminar.
Okay. Thank you all.
Thank you.
Thank you.
Hello.
I found it very strange when I talked